So today we will actually go through the tutorial which I actually shared with you last week. So that actually includes the questions mainly from the cylindrical systems as well as uh, with and without heat generation. Okay. So we will not be actually saving this lecture. So those who want, they should actually write it down. Okay. As I mentioned earlier, so the tutorials we will not be actually saving and sharing. Okay. Can we start?
Yes, sir.
Yeah.
Yes, sir.
Okay. So all these questions are actually simple questions only. Only that you have to actually find the logic in which we have to actually do this. So we'll actually get the logic only by solving as many problems are actually possible. So once you actually see the solutions, you will actually understand that this is actually very simple questions we are talking about. Okay. So, but in order to have the logic, you must actually solve as many problems are actually possible. The first one, so radioactive wastes are actually packed in long, thin-walled cylindrical containers. The waste generate uh, thermal energy non-uniformly according to the relation Q star is equal to Q0 into 1 minus R by R0 square, where Q star is actually the local rate of heat generation and Q0 is actually some constant and R0 is actually the radius of the container. The steady state conditions are actually maintained by submerging the container in a liquid which is at T infinity and provides a uniform convection coefficient H. Obtain an expression for the total rate of heat generation per unit length and also use this to obtain an expression for the temperature Ts of the container wall. Okay. um, so if you see, this is actually our system. Okay, a cylindrical systems. In a cylindrical system, we are actually saying our nuclear fuel or a nuclear waste is actually going to be filled. Okay. And we are not talking anything about the thickness of the. We are not talking anything about the thickness of the container. So we can actually assume the thickness to be actually negligible. So only that there is actually a container inside that it is actually going to be the a nuclear waste, and this is actually generating heat also. But yeah, if you actually remember, we actually derived our equation for cylindrical systems with heat generation. And yeah, cylindrical system with heat generation. Uh, yeah, here you can actually see that this is our basic governing equations. Okay. So, and we actually integrated it and we actually got our temperature profiles and all those things. Can we actually use the same equation over here? If in one case it is actually asked, the second question is actually to find the temperature on the surface. Can we use the same equation? Whatever we actually derived it over here. Can we use the same equation? Is the question clear? Is the question clear to everyone?
Yes, sir.
Yeah. So can we actually use the same equation? The same equations can we actually use? We cannot actually use because here we actually assumed it actually be a uniform heat generation, right? We actually assumed it to be a uniform heat generation. So that's why when we actually integrated it over here, we actually assumed the Q to be actually or the heat generation to be uniform and all. So based on that, we actually got some temperature profile in the solid or within the system. But here it is actually written as the heat generation itself is actually a function of R. Okay. So in order to find the temperature profile within, You cannot actually use the basic equation whatever we actually said. Obviously, the governing equation is actually going to be same. So only that the integration is actually going to be different. So instead of simply writing the q, you have to actually write it q into q0 into 1 minus r by r0 square. Okay. So you have to actually do that. And if you are actually doing this, then you can actually see uh, what is actually the temperature profile within the system you can actually get. So what are actually the boundary conditions? So boundary condition is it is actually solid cylinder. So basically at the center, what is actually the boundary condition? Two boundary conditions will be having, right? At the what is actually the boundary condition at the outer surface? It is actually the convective boundary condition. And what is actually the boundary condition at the center point, center axis? What was actually the boundary condition we actually used for a heat generation cylinder with heat generation? We actually used the symmetry condition, right? We said that it is actually going to be maximum at the center. So therefore, what we are actually going to take is actually the symmetry condition. So dt by dx is equal to 0 was actually the boundary condition. The boundary conditions are all same only that the integration is actually going to be different. So you will actually get a different temperature profile. Okay. So that way you can actually do this. And then another question was that obtain an expression for the total heat rate at which energy is actually generated per unit length of the container. Okay. So one method is that so once we actually do this, um, you will actually get the full temperature profile within the system. Okay. And what is actually the total heat generated within the system? So that we can actually say that whatever the total heat generated within the system, that is actually convected out, right? So therefore, we can actually, once we actually get that full temperature profile within the system, we can actually say that minus k dt by dx at x is equal to, or dt by dr at r is equal to r0. Minus k dt by dr at r is equal to r0. If you actually do that, then you will actually get the maximum heat, or it is actually the total heat that is actually being convected out. Okay, so that is actually the total heat generated within the system. So that is actually one way you can actually do this. The regular method, or the or based on the governing equation, that's how you can actually do that. Okay, so another method is that so here it is actually directly given how the heat generation is actually there along the length. Okay, so and here in the question it is asked what is actually the total rate. So it is just a matter of integration. So here for a small strip, how much is actually there? It is actually given. Okay, so what you have to do is you have to actually integrate it over the full cylinder. So if you are actually doing that, yeah, here it is actually given. The heat generation is actually going to be heat generation per unit volume into dV. Okay. So heat generation per unit volume is actually what it is actually given for us, but it is actually non-uniform. So you have to actually integrate it. So whatever it is actually given is actually for a small strip. So what is actually the volume for the small strip is 2 pi r into dr into L. L is actually given as length. Length is actually given as 1 meter or 1 centimeter, whatever it is. Okay, so you can actually integrate it. So Q star into 1 minus R by R0 square. So that is actually the volumetric flow rate, heat generation into the volume for the small strip. Okay, so 2 pi r dr into L. L we can actually take it as 1. So here it is a simple integration we can actually going to have. R is actually going to come inside the bracket. Okay, so this R, it is actually going to come inside the bracket. So, and if you are actually doing the integration, you are actually going to get a symbol. You are actually going to get a symbol expression. So that is actually the total heat generated. As I said, the same relation you will actually get by getting the relation such that first you have to actually find the full temperature profile using the boundary conditions. and then you have to actually calculate minus k dt by dr at r is equal to r0. If you actually put that, you will actually get the same expression. Okay. Yeah. So next question, next part is actually use this result to obtain an expression for the temperature Ts of the container wall. So temperature surface or the temperature on the surface. We have first of all we actually assume the thickness of the cylinder to be actually yeah, thickness of the wall to be actually negligible. So it doesn't matter whether it is actually inner temperature or outer temperature. Okay. So there are actually again two methods. First of all, you can actually find the full temperature profile as we said using the boundary conditions and all. So into that you have to simply put R is equal to R0. Then you will actually get the temperature on the surface. So another method is we actually already discussed this, right? If you are actually having a convective boundary condition, what you have to actually see is we already found what is actually the total heat generation, right? So we already found what is actually the total heat generation by integration method. So that is what actually convected outside also, right? So Q, whatever is actually generated, that need to be actually conducted because we are actually saying it is actually steady state condition. So Q generated is equal to H A surface into T surface minus T infinity. And A surface is equal to 2 pi R0 into L. And Ts is actually there. And we know what is actually H. We know R0. L, we are actually taking it as one unit. T infinity also we actually know. So therefore, you can actually write Ts in terms of this. Okay. And what, yeah. And Q generation, we actually found already as this time pi into q0 star into r0 to r0 square by 2. Okay. Yeah. So that's how you can actually find the total heat generation as well as the surface temperature. So as I said, there is actually more than one method for this. You can go with the basic governing equation itself. So that is actually one method that is actually a bit lengthy and all. So this is actually some tricky method you can actually use. Okay. So any doubts in this? Is it clear? Should I actually repeat again? Is it clear?
Yes, sir.
Yeah. So now we can actually go to the second one. Yeah. So this is actually a thermal resistance one for a cylindrical systems. A steam flowing through a long, thin-walled pipe main, pipe maintains the pipe wall at a uniform temperature of 500 Kelvin. Okay. Thin-walled pipe means that pipe is actually having no thickness at all. So whenever you are actually seeing some thin-walled, etc., and if it is thickness is actually not mentioned, then you can actually assume it to be a negligible thickness. Okay. In that case, the internal resistance, conduction resistance through that pipe itself can be actually neglected. Maintains the pipe wall at a uniform temperature of 500 Kelvin. So there is no inner temperature, outer temperature or something. The pipe temperature is actually at 500 Kelvin. The pipe is actually covered with an insulation blanket comprises of two different materials A and B. Okay. So figure is actually given. So now two materials are actually there, A and B. Okay. So interface between the two materials may be assumed to have infinite contact resistance and the outer surface is actually exposed to air of T infinity and H. Okay. So what it is actually written over here is, here we are having two insulation materials A and B. Okay. And the contact resistance between A and B is actually given as infinite. Okay. So what is actually significant for that? Why it is actually given as an infinite thermal resistance? Because if the resistance is only finite, what happens is that there is actually going to be a heat flow from B to A. Okay, so in that case, there is actually going to be a temperature gradient in the azimuth direction, circumferential direction. there is actually going to be a temperature gradient. Okay, so in that case, it is actually going to be a 2D conduction, and we cannot actually do any further analysis. Okay, the same actually goes for our simple slab condition also. In a slab condition, whenever you are actually going to have a parallel resistance, then the contact resistance we are actually assumed to be actually infinite between the parallel walls. Okay, not the series walls. Between the parallel walls, we have to actually assume the contact resistance to be actually infinite. Okay, so then only there is not going to be any heat transfer between the parallel walls. Okay. So here, therefore, we can actually assume this to be two sections, A as well as B. Okay. So the questions are actually asked us, sketch the thermal circuit, and we have to actually find what is actually the total heat loss from the pipe and the temperatures at the outer temperatures, Ts and A and B surface temperatures. Okay, yeah. So it is actually, we can actually see that it is actually a circuit. First of all, we can actually see that there is no pipe thickness. Pipe is not having any thickness. So we can actually assume the contact resistance only for the insulation. So this is actually kind of an insulation we are talking about, A and B. Okay. Is it given as insulation itself, right? Yeah, insulation. It is given as insulation itself. So A and B are actually the insulations, and therefore the thermal resistance are actually only for this A and B, and obviously the convective resistance at the outer surface. Okay. So the conduction resistance is actually only through the insulation, and since the pipe thickness is actually given as negligible. Okay. So since we can actually see how to tackle this one, so basically we can actually go for a parallel resistance mode. Okay, so parallel resistance we are actually going to consider. So we are actually considering obviously a unit resistance. So what is actually the thermal resistance for a cylinder? What is the thermal resistance for a cylinder? What is the thermal resistance for a cylinder? Thermal resistance for a cylinder is actually given as ln R2 by R1 divided by 2 pi. Okay, where is that? Yeah. So ln R2 by R1 divided by 2 pi Lk. So L in this case, we are actually assuming it has to be 1. Okay. So R2 is there, R1 is there. Can we use this one itself directly for the section A as well as B? Can we use this relation directly to A as well as B?
No, sir.
Yes, sir.
We need to change the area
Yeah, very good. So how can we actually change the area? Where is the area comes into picture over here?
denominator.
Denominator. So here we said 2 pi Lk because if you remember, we are actually assuming that to be the that to be the surface area, the cross-sectional area we actually said, okay, for any strip, and then based on that we actually got that. But in this case, we can actually see that only the half circle is actually going to be there. Only the half circle is actually going to be there. Okay, so therefore instead of 2 pi r you have to actually go for pi r. Okay, so therefore in the denominator instead of 2 pi we have to actually write ln r2 by r1 divided by pi lk. Okay, so that is actually going to be the resistance for this half section. So if the section was only there were actually 4 material, then we have to actually go for pi by 2 for each case. Ln R2 by R1. Ln R2 by R1 is actually same for all the conditions. Ln R2 by R1 divided by pi by 2 L into K. Okay. So in this case, anyway, we are actually having this half circle. So we have to, we don't have to go for pi by 2, only that the 2 itself is actually going to be reduced from the denominator. So here you can actually see the two parallel resistance we are actually going to have. So first, we can actually assume it actually starts from here. right? So in a temperature, it is actually given as 500 Kelvin. So from here, through the material, through the surface, one resistance is actually there. And then after this, there is actually going to be one resistance. So likewise here also, so through the insulation, one resistance, and after this, convection resistance. Okay. So that's what it is actually written over here. So TS1, from TS1 to T surface B. Okay. And after this, you are actually going to have the next resistance. Okay. So here also from TSB, TS2B, from here again we are actually going to have the second one. Okay. So convection resistance, first conduction through the insulation material A, and then convection from material A. So next one, convection to material B, and a conduction to material B, and convection through a convection from the material B. Okay. So both these things are actually, yeah, for each material, the conduction and convection are actually serious, and but altogether it is actually parallel to the other material. Okay. Yeah. So now everything is actually, so once we actually draw the circuit, everything is actually going to be same. So you have to actually simply write it in terms. So we know almost all the terms, but we don't know what is actually TS1 and TS A and TSB. We don't know. Okay. But that is actually okay. So, but yeah. So the total heat flux is actually the heat through the material A, and then heat through the material B. Okay, heat through material A and heat through material B. Yeah, so that's what we are actually calculating separately. TS1 is actually 500 and T infinity is actually 300. We know all the other terms. So ln R2 by R1, we know pi into K material. For A material, the conductivity is given as 2 watt per meter square Kelvin, and 1 by HA. Okay. Yeah, here also again the convective resistance. So convective resistance also we are actually going to have 1 by HA, right? 1 by H into area. So if it is a full circle, we are actually saying 2 pi R2, R2 into L. So L anyway, we are actually taking as 1. But since we are actually talking about only half circle, so instead of 2 pi R, we are actually taking only pi R2. Okay. Yeah. So that's why here we are having pi R2 into H. So that is actually the that much is actually the heat generator or heat actually travels through the material A, 842 watt per meter. Okay, so we are actually talking about per unit length. So that's why it is actually given as watt per meter. So likewise for material B also, total heat transfer is actually 198 watt per meter per unit length. So the from here we like get what is actually the total heat loss. The total heat loss we are actually getting as 1040 watt per meter. Okay, so that's how it is actually going to be done. So that is actually the first question. Yeah, the thermal circuit is actually the first question, and second part was what is actually the total heat, then what are actually the outer surface temperatures. So once we actually get the A and B, then you can actually put it into the equation here itself. Okay? So instead of uh, yeah, so instead of going from a TS1 to T infinity, you can actually say TS1 to TS2 A. So in that case, you have to actually consider only the conduction resistance to material A. So in order to find the temperature, surface temperature on material B, you have to actually pass from TS1 to TS2B, and the conduction resistance to material B. Yes, so separately you can actually do that. Yeah, here. So QA, it's actually same only, right? Whatever the heat, uh, total heat transferred to A, that is actually the same for whether it is actually we are considering for a full resistance or half resistance. So from with these equations, you can actually get what is actually TS2A, right? And yeah, we're considering TS1 minus TS2A divided by ln R2 by R1 pi into KA. So if you're actually doing that, all the terms we know now. So Q also we actually calculated using the full circuit, and based on that you can actually calculate what is actually the outer temperature. Yeah. Uh, yeah, likewise, we can actually also calculate what is actually the surface temperature on B. So here only the conduction resistance through B is actually going to be considered. Okay. Yeah. So any doubts in this?
No,
Okay.
sir.
So now we are moving to the third one. An electrical wire having a radius of 5 mm, electrical wire having a radius of 5 mm, so it is actually a solid wire, and a resistance per unit length 10 raised to minus 4 ohm per meter, is coated with a plastic insulation of thermal conductivity 0.2 watt per meter Kelvin. Okay. The insulation is actually exposed to ambient air of air for which the temperature is 300 and H is equal to 10 watt per meter square. If the insulation has a maximum allowable temperature of 400 Kelvin, what is actually the maximum possible current that may be passed through the wire? So an electrical wire is actually there. Its diameter is actually given. The copper wire diameter is actually given. Its resistance is actually given, and it is said that it is actually having a plastic coating. Okay, so it is actually, yeah. So this is actually inner one, a clear one is actually the wire, and it is actually having a plastic coating. Okay, so what is actually asked is if the maximum temperature allowable on the insulation is actually 450 degree or 450 Kelvin. So what is actually the maximum current that can be actually passed? Okay. So first of all, where is this maximum current will be actually coming? At the radius R1 or R2? Where is this maximum resistance coming or maximum temperature coming? At the insulation inner temperature or outer surface?
Inner one, sir.
Inner one. Yeah, very good. So what is actually asked is, so here we are actually talking about an insulation, but is this insulation an thermal insulation or electric insulation? It is actually an electric insulation we are talking about. Okay, but for this particular case, even though we are actually not explicitly saying as electrical insulation, it is actually the electrical insulation we are talking about. And what we want is actually the maximum heat loss to the ambient. The insulate for a thermal insulation, we are actually assuming or we are actually wanting such that the maximum heat or the minimum heat loss to the ambient. But in this particular case, since we are talking about the electrical resistance and all, or electrical wire and all, we are actually trying to find what is actually the, or we want the maximum heat loss to the ambient. Okay, so we want the maximum heat loss to the ambient. So, what do you actually think? Means, is there any particular term regarding this maximum heat loss to the ambient and the radius of the insulation or something? What is that particular term called? Is there anything that actually relate this uh, radius of the insulation and the maximum heat transfer through the ambient or something? Have you actually did something on that?
Sir, infinite length.
No. That is actually for the fins and all. Right? For an insulation, did we say anything on the maximum heat loss to the ambient and its particular radius and all? Did we actually do anything on that? Does anyone remember this term called critical radius? Critical radius of insulation. Does anyone remember? Do you remember this?
Yes,
Critical
sir.
radius. Yeah. So critical radius, that is actually the radius at which the heat loss to the ambient is actually going to be maximum, right? Yeah. So we said that for an insulation, there is actually going to be two resistance. One is actually the conduction, right? So when we are actually increasing the thickness in insulation, thickness of the insulation, the resistance, conductor resistance is actually going to be increasing, but the convective resistance is actually going to be reducing because the surface area is actually going to be increasing. Okay. So because of this contradicting, so because of this contradicting behavior, so there is actually going to be a particular radius in which the total resistance is actually going to be less or going to be the lowest. Okay. So that radius is actually the radius of insulation in which the heat transfer is actually going to be maximum. Okay. Yeah. So we said that for a thermal insulation, therefore, we need to actually put the radius much above the critical radius. Because at the critical radius, the heat transfer is actually going to be maximum. Heat transfer to the ambient going to be maximum. But in this particular, so therefore, a thermal insulation, we need to actually have a radius much above that of the critical radius. But in this particular condition, in this particular question, what we are actually saying is that we are actually talking about a thermal wire, and we are actually saying the insulation should be actually having a maximum temperature of 450 or something. Okay, so but we need to actually pass the as much current as actually possible. That means we should be actually making our insulation such that its critical radius, it should be actually of its critical radius. Okay, so therefore the cooling or the heat transfer from the inner wire to the ambient is actually going to be the maximum possible. Okay. So with a since the maximum heat transfer is actually going to be maximum possible, so with a particular temperature, inner temperature for the insulation, we can actually pass maximum possible current or maximum possible heat. Okay, so therefore we can actually pass the maximum possible current through that. Yeah. Yeah. So if you see the values, it is actually given as the electrical wire radius is actually given as 5 mm, but the outer diameter is actually not given for the insulation. Okay, so because that is actually the critical radius we are actually talking about. If you are actually giving our if you are actually giving our insulation thickness to be actually the critical radius, so that we can actually see that our radius is actually or heat transfer is actually going to be maximum. But what is actually the critical radius? What is actually the equation for critical radius? Can anyone tell me?
K by H.
K by h. Very good. So what is actually K by h over here? K is actually zero point 0.2 and h is actually 10, right? K is equal to zero point 0.2 and h is equal to 10. So what is actually the radius? It is going to be 0.02 meter. So into 1000, if you actually say point 20 mm, right? Yeah. So we can actually say that the critical radius is actually 20 mm. So inner wire is actually 10 mm and the critical radius need to be actually 20. So we can see that the figure is obviously not of the scale. Okay. So wire is actually going to be very small, only 5 mm, whereas the critical radius is actually going to be 20 mm. So if you are actually putting an insulation of that much thickness, so you are actually going to have the maximum possible, then you are actually going to have the maximum allowable current. Okay. So we know now what is actually the R1. We know now what is actually R2 because R2 is actually the critical radius. And we know what is actually the inner temperature, right? So inner temperature we actually know, T1 we actually know. Yeah, T infinity we know, H we know. So everything we actually know. Okay. So therefore we can actually write as a electrical resistance circuit. Okay. So H1 minus T1 minus T2 So what are actually the resistance? Conduction resistance to the insulation and the convective resistance. Okay. And what is actually the heat flux? Heat flux is actually going to be I square R, right, per unit length. So the conductivity is actually the resistivity is actually given. So ohm per meter unit length. Ohm per unit length is actually given. So I square into ohm. I square into R directly is actually given. So that is actually the total heat flux or total current. Okay, and we know what is actually R2. So from there directly you can actually calculate what is actually I. Okay, yeah. So that's how you can actually do this. So whatever written over here is actually something different, but this is actually the method in which we can actually do. So this is actually the logic behind that. Yeah, this is actually the circuit. So first conduction resistance and the convective resistance, and total current, total heat passed is I square R T1 minus T2 divided by R1 plus R2. Okay, yeah. So that's how you can actually do that particular problem. So next one, the cross section of a long cylindrical fuel element in a nuclear reactor is actually shown. Yeah, cross section is actually shown over here. So it is actually having, this is actually the fuel and this is actually the cladding, thin aluminum cladding. So here again the thin is actually given. So that means its the thickness is actually negligible. Uh, So energy generation occurs uniformly within the thorium fuel load, which is actually of diameter d is equal to 25 mm. So here uniform heat generation is actually given. Okay. And it is actually warped in a thin aluminum cladding. Thin means again its thickness is actually negligible. It is proposed that under steady state condition, the system operates with a generation rate of Q is equal to 710 raised to 18 watt per meter cube, and the cooling system characteristics of T infinity 95 degrees Celsius and H of 7000 watt per meter square Kelvin. Is this proposal satisfactory? Okay. So what is actually the question saying? We are having a system like this. So it is actually having a fuel rod and with a particular generation rate. And if you are actually giving a particular cooling rate, so it is actually asked whether the system can be actually put in a safe manner. That is actually the question. We can just do the calculation and we can actually see. So here the heat generation is actually given per unit volume. Okay. So therefore, and the diameter is also given. Okay, so from there you will actually get what is actually the total heat generation. So only that whatever the total heat generated is equal to the total heat convected. Okay, that is actually our basic understanding. So here we are actually saying by energy balance, so total heat input into the cladding from the fuel is equal to the heat loss from the cladding. So total heat generated is Q into Q is actually the heat generation per unit volume. And what is actually the total volume? Total volume is pi r square L. Okay, so L, if you want, we can actually keep it as unit length, or we can see that it will actually cancel off also. So since we are actually saying the thickness is actually negligible of the aluminum cladding, so it is actually having some thickness, it is actually negligible. So whatever the heat coming in, it is actually going out. So the diameter of the cladding, outer diameter as well as the inner diameter, can be actually given as the same diameter d. Okay. So what heat loss by the cladding to the coolant. So that is equal to HA into delta T. So H into 2 pi R1L. So since the diameter we are actually, or the thickness of the cladding is actually assumed to be 0, we can actually write surface area is equal to again 2 pi R1 into L into T wall 1. That is actually the temperature of the cladding minus T infinity. Okay. So if you actually do this, you can actually get the expression for the wall temperature on the aluminum cladding. Okay. Wall temperature of the aluminum cladding we will be actually getting, and yeah. We know all the terms. T infinity we know, heat generation rate we know, R1 we know, H we know. Okay. So based on that, if you are actually doing the calculation, what you are actually going to get is 993 Kelvin. Okay. So unfortunately, this is actually more than that of the softening point, or at least the melting point of the aluminium. Okay. So since it is actually more than the melting point of aluminium, is this satisfactory? Well, this system is actually not satisfactory. We have to either reduce the ambient temperature, okay, or we have to actually increase the H, heat transfer coefficient. So how can we actually come up with that? So from here, from this equation, we can actually see that, yeah, here, if you're actually reducing the ambient temperature, then wall temperature is actually reduced, or we have to increase the increase the heat transfer coefficient, so that the full term is actually going to be reduced, so that the ambient temperature or the wall temperature is actually going to be reduced. Okay. Yeah. So that is actually the method in which we can actually do this. Okay. So this is actually, we can see it is actually very tricky one, but it's actually very simple. So by doing more and more of this kind of exercises, you will get the better idea. Is that clear?
Yes, sir.
So next one, yeah. A plain wall of thickness 0.1 meter and thermal conductivity 25 watt per meter square, having a uniform volumetric heat generation rate 0.3 megawatt per meter square, is actually insulated on one side, while the other side is actually exposed to the fluid at 92 degrees Celsius. The convective heat of coefficient between wall and fluid is given. Determine the maximum temperature in the wall. Okay. So here it is actually we have actually reduced that, or we have actually done that derivation, right? Yeah. To a wall with 1D with heat generation. Yeah. So 1D with heat generation, we have actually done that, right? So we said that we are actually going to have a system in which T1 and T2 are actually there on both either sides, right? So later we said that if the temperatures are actually going to be same, we are actually going to have a particular, we are actually going to have a symmetry at the center. So therefore, we can actually keep it such that one side is actually insulated and other side is actually open, right? Or constant temperature condition we actually say. So based on that, we actually derived our condition, and later we actually said that if convective boundary condition is actually there, based on that we can actually write our surface temperature based on these things, and we can actually modify our equation based on that. Okay. So this is actually our, if you remember, this is actually the basic equation we actually derived, with the one side insulated, or we can actually say inner side or the center side actually insulated, and the outer side having a convective heat transfer. Okay. So the same condition, same equation we can actually use. So it is actually given the insulation side, while the other side is actually exposed to the ambient. So determine the maximum temperature in the wall. So maximum temperature, obviously, it is actually going to happen at the insulation side. Okay, so wherever the insulation is actually there, so there it is actually going to be having. So here we actually derived our situation or derived our equation such that insulation is actually at the point where x is equal to 0, right? So therefore into our this equation we have to actually put x is equal to 0. So then you are actually going to get the maximum temperature. Obviously, you can actually do the other way also. You can actually say. Uh, So we can actually say that I am actually going to put such that I am actually going to put my insulation boundary condition at x is equal to L. Okay, so in that case, this wall expression will be actually different. Okay, so but if you are actually putting x is equal to L, then you are actually going to get some temperature. That temperature value is actually going to be same, maximum temperature. Okay, yeah, is that clear? So because we already have derived that equation, and that's why I'm actually taking less time. If you see, this is actually going to be the temperature profile. Okay, so this is actually going to be the temperature profile, and maximum obviously comes at the insulation point. Okay, here you can actually see that in our lecture, what we actually did is first we actually said a constant temperature boundary condition. We actually assumed our system to be a constant temperature boundary condition at one surface, and at the middle it is actually going to be the symmetry condition. So based on that, we actually derived our equation in terms of yeah. So yeah, we derived our equation 23 based on the surface temperature. So later we said that if you are actually instead of a constant temperature boundary condition, if you are actually going to a convective boundary condition, then we said that whatever the heat generation is actually going to be convected out, and then we wrote this surface temperature in terms of heat generation and ambient temperature, convective condition, etc. And we actually put into the equation 23, and we put it into equation 23, and we got another equation. Right? So this same equation we can actually derive directly by applying the boundary condition as convective boundary condition. If you are actually putting one side boundary condition as insulation and the other side as convective boundary condition, so directly also you will get the same expression. Okay. The same expression you will actually get. Okay, so into that you have to actually put wherever the x value to which you have actually assigned the insulated boundary condition. Okay. Yeah. So that's what you can actually find for the plane wall condition. So next one, next one is actually a bit tricky. So here, find the steady state heat flux through a infinite composite wall. Infinite means on one side, on top and bottom, it is actually going to be infinite length, made up of two materials. Also find the interface temperature Ti. So only that it is actually very simple. If you actually see this, it is actually very simple. We have the temperature on both sides. We have the thermal conductivity, or we have the thickness is actually given. So with a thermal resistance analogy, we can actually simply do that. But the catch is that the conductivity is actually going to be a function of temperature. So therefore, we can see that the resistance, to actually analyze, the resistance is actually going to be a function of the voltage, right? The resistance is actually going to be a function of voltage. So in that case, obviously, we cannot actually go with the thermal resistance analogy. Okay. So the two materials are actually there, M1 and M2. It is having two different conductivities. Okay, but the conductivity again is actually a function of temperature. So we cannot actually go with the thermal resistance analogy, but we can actually obviously we can actually go with the energy balance. Energy balance is actually going to be there. That is actually the first law of thermodynamics itself. So based on that, we will see whether we can actually go with something. Okay. So this is what we can actually see it over here. So M1 and M2. We know that since there is no heat generation of something, the heat flux is actually going to be same throughout. Okay, so whatever the heat flux through material one should be actually same as that of the heat flux through that, because the height or the cross-sectional areas are actually going to be same. Yeah. So if you actually see Q1 separately, so Q1 we are actually writing minus K1 dt by dx, right? But K again, it is actually a function of temperature. K is actually given as 0.05 into 1 plus 0.0080, where T is actually the temperature. Okay. So here, what we are actually going to do is, uh, we have no other option but to integrate it. Okay. So what is actually the meaning for that? We cannot actually say anything. Okay, so there is no particular meaning or something, but since T is actually going to be there, so in order to tackle this differential and the constant temperature term over here, so in order to tackle that, we are actually going to integrate it. Okay, so first we are actually going to integrate for the material one for its thickness of 5 centimeter or 0.05 meter, and temperature it is from or here it is 600 to T interface temperature. Okay. Temperature integrating from a 600 to interface temperature, length from 0 to 0.05 meter. Okay, so that's what it is actually integrating. So we are actually going to get Q1 as a function of Ts. Okay, because here only the Ts is actually going to be there. So Q1 heat flux 1 we are actually going to get as a function of Ts. Okay. So again the same thing we are actually going to do with the Q2 also. So Q2 therefore we are integrating from 0 to 10 centimeter, that means 0.1 meter, and the temperature integrating from Ts to 30 degrees Celsius. Okay, temperature integrating from Ts to 30 degrees Celsius. Okay, so length from 0 to 0.1 and Ts to 30 degrees Celsius. So if you do that again, you are actually getting another 10. But we know that QS, uh, yeah. So we know that Q1 is equal to Q2. So if we are actually going to equate this, you are actually going to get TS as nearly 500 degrees Celsius. Okay. Yeah. So then you have to actually put it into this equation two, Q1 flux or Q2 flux. You are actually going to get what is actually the heat flux through the system. Okay. Is that clear? So
Yes, sir.
yeah. Okay. Now the last one. This is one minute. So last question. An electric current I pass through a pipe pass through a pipe of inner and outer radii R1 and R2. So that means it is not passing through a wire, but it is actually passing through a pipe, hollow pipe. The electric resistance per unit length is actually given as R. The pipe is well insulated on outside and subjected to a constant temperature Ti on inner surface. Determine the form of steady state temperature distribution in the pipe. Okay, this is a cylindrical system with heat generation. Okay, but if you remember the cylindrical system with heat generation we actually conducted, but for that if you remember we actually said it is actually for the solid cylinder. Okay, heat cylindrical system with heat generation we actually said it for a solid cylinder, and for that we said that at the center we are actually giving the boundary condition as symmetry boundary condition. Okay, but for a steady state condition without heat generation we actually considered it for hollow cylinder, because we said that for a solid cylinder steady state heat conduction without heat generation is actually not possible, because for that there need to be a heat in and heat out in the radial direction. If it is a solid cylinder that is actually not possible, but for the with heat generation we actually consider it for a solid cylinder only. We didn't do any analysis for the pipe or a hollow cylinder. Okay, so that's why this question is actually included over here. Okay, so here this is actually the condition. So it is having inner radius R1, outer radius R2. Okay, the boundary condition is such that at the outside dt by dx is actually 0, and inside boundary condition is at r is equal, yeah, here at r is equal to R1, t is equal to T1. At r is equal to R2, dt by dr is equal to 0. Okay, so these are actually the boundary condition. And what is actually the basic equation? Basic equation is 1 by r d by dr into r into dt by dr is equal to minus q by k. Okay, but q we can actually keep it as like this is because it is actually uniform heat generation. Okay. And it is actually constant value. And what is actually the total heat generation? Total heat generation per unit volume is I square R. I square R is actually the total heat generated. So divided by the volume. What is actually the volume? What is actually the volume? Volume is actually cross-sectional area into length. What is actually the cross-sectional area for a hollow cylinder? It is equal to pi r square outer radius square minus inner radius. Outer area square minus inner hollow area square area, right? So therefore, pi into r2 square minus r1 square. So that is actually the cross-sectional area of the hollow cylinder into into length L. So we are actually assuming it for a unit length. So we can actually give it as L is equal to 1. Okay. But again, you can see I, R, R2, R1. So all are actually constant values only. It is not a function of radius. So we can actually, in our basic equation, we can actually keep our Q as actually constant itself. Okay, you don't have to write the expression for this. If it was actually varying with R, then definitely you have to actually keep it in the basic equation itself so that integration will be actually done properly. Okay. Yeah. So in this particular case, R is actually constant. So the basic regular conditions we have to actually go with. Yeah. Here we can actually see that yeah, we have to actually integrate it twice. So integrate it twice, then you are actually getting the temperature table like this. So we are actually having C1 as well as C2. Okay. And then we are actually going to apply the first boundary condition, R is equal to R2, dt by dr is equal to 0, right? So if you are actually going to put it into that, you are actually getting some C1 value. Okay. So here you can actually see that C1 into ln R. Ln R is actually coming. So for a hollow cylinder, again, you can actually remember that the same kind of expression was actually coming. Okay. Same expression was actually coming, right? So here, Q by 4K R square plus C1 ln R plus C2. So here also, for a solid cylinder also, Q by K minus Q by K R square by 4 C1 ln R plus C2. Okay. But here, for a solid cylinder, we said that but the dt by dr also, dt by dr is equal to 0. That's what our first condition was. But again, we said that the logic is that at center, okay, since it is actually a solid cylinder, R is actually coming to be equal to R0 at the center. So ln0 is actually undefined. So only way is that C1 should be actually go to equal to 0. Okay. But by putting the boundary condition also, we actually got the same condition. But here we can actually see that C1 is actually not going to be equal to 0. Okay, C1 is actually having some value. So therefore, this ln term is actually going to be here. Okay. Yeah. And then the next condition is at R is equal to R1, T is equal to T1. So if you are actually going to put that, you are actually going to get what is actually the C2 value. Okay, C2 value, it's actually a bit lengthy. So, but you can actually go give it into that. Okay, so if you're actually putting that, you are actually going to get the nice expression. Again, if you want to expand this, you can actually write what is actually the qi. So qi, we actually found what is actually I square r by pi r1 square minus r2 square. Okay, so if you're actually putting into that, again, you can actually have a little bit of simplification. Okay, but if you're actually putting that, then it is actually not a general expression. So this expression, whatever we are actually shown over here, so that is actually applicable for any heat generation, okay, for through a hollow cylinder. Right? For this particular condition where Q is equal to I square R by pi R2 square minus R1 square, you can, if you want, you can actually put it into this again. Okay. Yeah. So that's how you can actually solve this temperature profile for the solid cylinder. Not solid cylinder, hollow cylinder with heat generation. Okay, again, this is actually a simple condition because we have actually put uh, yeah, we have actually put a insulation boundary condition over here. So if you are actually saying that inner temperature at T1 and outer temperature at T2, again, you can actually do the same thing, but the expressions are actually going to be a bit lengthy and the algebra is actually going to be a little bit messy. But obviously, you can actually do that. Okay. So till here, the basic equation till here, till equation 3 is actually going to be same whatever the boundary condition it is going to be. But the final equation, it takes the shape by taking the input from the boundary conditions. Okay. Yeah. So these are actually the some questions, some nice questions I could actually find for from this heat generation as well as the cylinder system point of view. Okay. Yeah. So next week I will actually try to upload some, or this weekend by tomorrow or something, I will try to send some questions from this fin point of view as well as uh, the transient point of view. Okay, and then we can actually discuss in the next class. Okay, but in Monday and Tuesday also I will not be actually able to take the classes. Okay, so any doubts in this? Okay,
No, sir.
okay, okay then, have a nice day too. So whatever the classes we lost, we will actually compensate it.
Yes, sir.
Okay, 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 thank you, have a nice day too.
Thank you, sir.